Hi there, and welcome to Tech with Shaping Pixel. In this video, we're diving into Part 8 of the Google Associate Data Practitioner full crash course, where we'll explore an introduction to Google BigQuery. If you haven't subscribed yet, make sure to hit that subscribe button and check out www.shapingpixel.com for the latest real exam questions and answer PDFs. If you want to analyze baby name trends across the United States, Google BigQuery is a powerful tool. To get started, open the Google Cloud Platform console and type BigQuery in the search bar to launch the service. Next, you'll need the right data. Click Add, search for Public, and select Public Datasets. Then, type USA_names to find the baby names dataset. Click on View Dataset to see the available tables. We'll use the first table for our analysis. Clicking on the table reveals its schema and a sample of the data. To start querying, click on Query and choose In New tab. The default query is incomplete, so type Select All to select all data. To find the most popular names, add Order by Number Descending and limit 10. Use the Format Query option for readability. Then click Run. The top result is Robert in New York in 1947 with 10,025 babies. To see only girls' names, add where gender equals F. Now, Mary in Pennsylvania in 1918 tops the list with 8,184 occurrences. BigQuery makes it easy to uncover fascinating trends in baby names. Next, check your query costs before running more analyses. Let's break down how BigQuery pricing works. There are two main components: storage and queries. Understanding these can help you manage your data costs effectively and avoid surprises on your bill. BigQuery's storage charges are impressively low. It costs just 2 cents per gigabyte per month, matching the price of cloud storage standard. If you don't edit a table for 90 days, the price drops to 1 cent per gigabyte per month, similar to nearline storage. Even better, with BigQuery storage, you are not charged for reading data, unlike nearline storage, which charges 1 cent per gigabyte for reads. If you are only using public datasets, you will not see any storage charges at all. The other cost is for queries. The first terabyte of queries each month is free. After that, it is $6.25 per terabyte, or about 2/3 of a cent per gigabyte. Query fees are based on processing, not where your data is stored. So whether your data is in BigQuery storage or cloud storage, the query cost is the same. For steady workloads, capacity-based billing offers predictable query costs, though storage is billed separately. For example, a query processing 163 megabytes would cost less than 1/10 of a cent if you exceed the free tier. To save query results in BigQuery, you first need a dataset. In the menu next to your project name, select Create Dataset and give it a name like baby names. You can also set a location for compliance or an expiration time if you want tables to delete automatically after a certain number of days. Click Create Dataset, and your new dataset will appear under your project. Now, run your query. Before executing, open Query Settings from the More menu and choose Set a Destination Table for Query Results. In the Dataset field, type Baby Names and select it. Enter a table name, such as Baby Names Top 10. Click Save, then Run. Your results are now stored in the new table, which you can preview directly in BigQuery. If you forget to set a destination, BigQuery saves results in a temporary table, cached for about a day. Rerunning the same query within 24 hours retrieves cached results, so you are not charged again. However, specifying a destination table bypasses the cache and incurs charges. To clean up, delete the dataset by clicking Delete next to its name. Confirm by typing Delete. This removes the dataset and all its tables. That's how you save and manage query results in BigQuery. BigQuery makes it easy to analyze public datasets, but what about your own data? Let's explore the main ways to load your data into BigQuery, whether it's from Google services or your computer. If your data is in Google Cloud Storage, Google Drive, Firestore, or Bigtable, you can import it directly. For files on your computer, use the BigQuery web interface. Just click Create Table, set the source to Upload, and select your file. BigQuery supports formats like CSV, JSON, Avro, ORC, and Parquet. BigQuery can automatically detect your table schema, but sometimes it guesses wrong. For example, if your file's gender column only has F at first, BigQuery might think it's a Boolean. In these cases, manually specify each field's type to avoid errors. For files larger than 100 megabytes, or if you want to upload many files at once, use the BQ command line tool. It lets you automate uploads and even use wildcards to load multiple files efficiently. You can also stream real-time data using the BigQuery Storage Write API, though streaming incurs a small cost. Remember, you cannot rename datasets, so choose names carefully. Now you're ready to load your own data into BigQuery. Sometimes you need to export data from BigQuery, especially if you want to use third-party tools. The most common method is exporting your data to Google Cloud Storage, then downloading it from there. Let's walk through exporting the baby names table. Click the table name, choose Export to GCS from the Export menu, and specify your cloud storage bucket and file name. You can export in formats like CSV, JSON, Avro, or Parquet. For this example, select JSON. Compression is optional, with gzip as the only choice. Click Save to start the export job. Once finished, check your cloud storage bucket for the file and download it to your computer. If your table is over 1 gigabyte, you must export it in multiple files. For example, exporting the games_y table in the baseball dataset requires adding a wildcard asterisk in the file name like gamesstar.csv.gz. BigQuery will split the export into numbered files automatically. To avoid ongoing storage charges, delete the exported files from cloud storage. Then return to BigQuery and delete any datasets you created during the process. Exporting from BigQuery is straightforward, but remember to shard large exports and clean up files when finished. Welcome to Loading Data into Google BigQuery. This lesson is designed for data engineers, data analysts, data scientists, and anyone preparing for a Google Cloud certification. By the end of this video, you will understand the essential methods for importing data in BigQuery. You will learn how to import records into BigQuery using several approaches. First, load jobs allow you to upload data directly from files or cloud storage. Next, you can use structured query language, or SQL, to insert data programmatically. The data transfer service automates data movement from external sources into BigQuery, making recurring imports easier. Finally, the Storage Write Application Programming Interface, or API, provides a high-performance way to stream data into your tables. After importing your records, you will discover how to clean up your data using Data Manipulation Language, or DML. DML enables you to update, delete, or insert records, ensuring your datasets remain accurate and organized. Before starting, it helps to be familiar with BigQuery, comfortable with SQL syntax, and have access to a Google Cloud Platform account. Please note, Google frequently updates its products, so minor discrepancies may appear over time. Google BigQuery is a powerful tool for building scalable data warehouses. capable of handling terabytes or even petabytes of information. But importing large volumes of data can be tricky. Let's break down the main methods for getting your data into BigQuery. First, there are load jobs. Think of these as BigQuery's data import wizard. You can add records to a new or existing table from local files or files in cloud storage. Supported file types include Avro, CSV, JSON, ORC, and Parquet. Alternatively, you can use SQL commands, specifically the load data command, to import records from one or more files. The supported file types are the same as with load jobs. Next, the data transfer service is designed for scheduled automatic imports. It can pull data from cloud storage, Google Apps, and even third-party platforms like Amazon Web Services or Microsoft Azure, making it ideal for recurring data transfers. The Storage Write API, part of the Google Cloud Software Development Kit, lets you build custom import tools. It supports both streaming and batch loading, giving you flexibility for real-time or bulk data imports. Finally, other managed services exist outside BigQuery. For example, Dataflow with Apache Beam enables streaming pipelines. DataStream replicates records and schema changes, and the BigQuery connector for SAP allows near real-time SAP data replication. Let us walk through how to import records into BigQuery using a load job, the simplest way to load data into a BigQuery table. We will use the Google Cloud Platform Web Console for this demonstration. First, log into Google Cloud Platform and navigate to BigQuery. Make sure you have a dataset ready, like Import Demo. Click the Add button to start a load job. Select your local CSV file as the source. BigQuery can automatically detect the file type and schema if your file includes column names in the first row. Just confirm your destination dataset and table name, then click Create Table. BigQuery uploads, parses, and inserts your records. For larger files, import directly from Google Cloud Storage. Select your dataset, click Create Table, and choose Cloud Storage as your source. You can specify a single file or use wildcards to select multiple files, such as all files starting with Steam dot and ending with CSV. Again, let BigQuery auto-detect the schema and create your table. After importing, review your table schema, details, and preview records. Load jobs are great for initial table creation or small batch imports, but they are manual and only support batch mode, not real-time streaming. If you want to import records into BigQuery using SQL, the load data command is your go-to tool. It is perfect for those who prefer SQL over the Google Cloud Platform Web Console for importing external files. To start, you can use the Create Table statement to make a new table or select an existing one. With load data, you specify the dataset and table where your records will go. For example, you might create a table called SQL command inside a dataset named Import Demo. Next, you tell BigQuery which files to import. You can choose from formats like CSV, and you specify the file locations using Uniform Resource Identifiers, or URIs. These URIs can point to files on Google Cloud Storage, Amazon S3, or Azure Blob Storage. And you can even use wildcards to match multiple files. Once you run the command, BigQuery will create the table and import your data. If your CSV file includes column names in the first row, BigQuery will automatically detect the schema and show you a preview of the imported records. Load data is great for batch imports and initial table creation, but it is a manual process. It does not support automation, scheduling, or streaming data imports, so keep that in mind for larger workflows. To import records into BigQuery using the Data Transfer Service, or DTS, you first need an existing table with the correct schema. DTS cannot create tables for you, so start by copying an existing table or defining your schema, then clear any unwanted records. Next, open the data transfer service in BigQuery. If prompted, enable the BigQuery Data Transfer API. Click Create a Transfer, select your data source such as Google Cloud Storage, and give your transfer a descriptive name to help you remember its purpose. Choose your schedule. Run transfers automatically at intervals as short as 15 minutes or select On Demand for manual execution. Specify your destination dataset and table, then select the files to import. Decide whether to append new records or mirror data, which replaces existing rows with the imported ones. You can also set options like deleting source files after transfer or skipping header rows in CSV files. Save your configuration. It will not run until you start it or the schedule triggers. Manage transfers easily. Edit, pause, delete, or run them instantly. DTS is ideal for reoccurring batch imports to existing tables. Let us explore how to import records into BigQuery using the Storage Write API. While this is not a step-by-step demonstration, we will cover the essential concepts and workflow you need to know. To get started, you will need to write custom code using a Google Client library. Google currently supports C#, Go, Java, Node.js, and Python for the Storage Write API. Once you have imported the appropriate library, you will create streams, which are central to the Storage Write API. Streams allow you to write records to BigQuery, and the process involves calling specific functions to manage your data flow. You can use the default stream for simplicity, calling the append rows function in a loop for each record. For more control, create an application created stream. This involves calling create write stream, then append rows for each record, and finally finalize write stream to close the stream. The Storage Write API is highly flexible. It supports both batch imports and real-time streaming, handles schema changes, and prevents duplicate streaming records. However, it requires significant coding experience and setup. For complex, continuous imports like telemetry data, the Storage Write API is invaluable. When you import data into BigQuery, it is common to encounter issues like blank fields, incorrect values, or duplicate records. The more records you import, the higher the chance that something needs to be fixed. To clean up your data, BigQuery offers a data manipulation language, or DML. DML is a subset of structured query language, or SQL, but requires you to use Google SQL. If you are using the legacy SQL dialect, you'll need to switch. There are 4 main DML commands: update, delete, insert, and merge. Update lets you fix or reformat records. Delete removes unwanted or duplicate records. Insert adds new records, and merge combines actions for more complex updates. There is also truncate, which removes all rows but keeps the table schema. For large imports, use a staging table. This temporary table holds new records separately, letting you review and fix issues before merging them into your main table. This approach saves time and prevents corrupting your existing data. Limit DML to cleaning and small changes, since BigQuery is not a transactional database. After cleaning, you can share your data securely using Analytics Hub, which helps you organize, advertise, and even monetize your datasets. Data is one of an organization's most valuable assets, so controlling who can view, modify, or delete it in BigQuery is essential. But access control in BigQuery is more nuanced than it first appears. BigQuery uses layers of access control. At the top are basic roles: viewer, editor, and owner, managed through Identity and Access Management, or IAM. These roles apply broadly across Google Cloud Platform services, not just BigQuery. However, basic roles are not very precise, so predefined roles are recommended for more control. Predefined roles in BigQuery can be assigned at the organization, project, dataset, table, or view level. They offer specific permissions like data viewer, data editor, and data owner, and can separate data access from job running permissions. For example, a job user can only start or cancel jobs, while a user can create datasets. To restrict access to certain data, use authorized views. An authorized view lets users see only the results of a query, not the underlying tables, which is useful for sensitive information. For instance, you can let a group see only specific columns by creating a view, granting them data viewer access, and authorizing the view to access the source table. Controlling access to sensitive data in BigQuery is crucial for security and compliance. There are two main approaches: using authorized views to hide sensitive columns, or implementing column-level access control with the Data Catalog service for more complex needs. With column-level access control, you start by creating a taxonomy in the Data Catalog service. A taxonomy is a hierarchical structure that classifies sensitive data. For example, you might have categories like high and medium, with high including credit card numbers and medium including IP addresses. Each specific type of sensitive data becomes a policy tag. Next, you grant access to specific groups based on these policy tags. For instance, you might give the accounting department access to credit card numbers by assigning them the Data Catalog fine-grained reader role on the credit card number policy tag. Access can be granted at broader or more specific levels depending on your needs. Then you tag the relevant columns in your BigQuery tables with the appropriate policy tags. Finally, enable the Enforce Access Control option in your taxonomy. Now, every query checks if the user is authorized to access sensitive columns. While authorized views work for simple cases, column-level access control with Data Catalog is better for managing complex or widespread sensitive data. It centralizes policy management, making it easier to protect data across your organization. Google BigQuery is built for speed and performance, making it one of the fastest data warehousing and analytics platforms available. But to truly unlock its potential, you need to know how to optimize your queries. BigQuery automatically generates indexes to speed up query execution. Its distributed architecture breaks up workloads and runs different parts in parallel, ensuring efficient processing. Additionally, BigQuery stores the results of recent queries in a cache, reducing the need to reprocess data when the same queries are run. Despite these features, your choices in storing and searching data play a major role in performance. The complexity of your queries and the number of columns and rows processed can significantly impact speed. To get the best results, use filtering as much as possible to minimize the data scanned. When using join clauses, select the most efficient join types and avoid expensive operations like cross-join. Be mindful of aggregate functions, such as sum, count, and average, as they can also affect performance. Sometimes, simply changing the order of SQL clauses can make a noticeable difference. Learning these optimization techniques leads to faster execution times, lower costs, and a better experience for your data analysts and engineers. Writing efficient SQL queries in BigQuery is all about reducing unnecessary work. The less data your query reads, processes, and writes, the faster and cheaper it will run. Start by using where, between, and limit clauses. Where clauses help you filter data, but for best performance, use them on columns like bool, int, float, or date instead of string or byte. Between clauses are great for filtering ranges, making your queries more readable and less error-prone. When working with clustered tables, limit can help you test queries without scanning everything. But remember, limit only reduces data read for clustered tables. Avoid using select star, which reads every column. Instead, specify only the columns you need. If you must use a wildcard, try select star except to exclude unnecessary columns. Also, avoid wildcard tables unless absolutely necessary, and always use the most specific prefix possible for better performance. Minimize joins, especially with large tables. Aggregate your data before joining, not after, to reduce the number of rows processed. Finally, break up complex queries into smaller, manageable steps using temporary tables or variables. Follow these strategies to write faster, more efficient SQL queries in BigQuery, making your data analysis smoother and more cost-effective. Boosting BigQuery performance is not just about writing efficient SQL. Leveraging caching can make a huge difference, especially for stable and frequently used queries, delivering faster results and saving on processing costs. Whenever you run a query, BigQuery stores the results in a temporary table for up to 24 hours, unless you specify a destination table. If you repeat the exact same query, BigQuery retrieves results from this cache, providing near instant answers without extra charges. To take full advantage of caching, ensure your repeated queries are identical, including parameters and identifiers. Standardize queries that only differ slightly, as even small changes can turn a cache hit into a miss. Remember, cache results may be invalidated sooner than 24 hours if reference tables or views are modified, so minimize changes and schedule them during off hours when possible. Caching does not work for queries using wildcard tables, external data sources, or non-deterministic functions. Also, very large result sets may require a custom destination table, which incurs storage costs. You can force BigQuery to use only cached results with the require cache flag in the BQ command line tool, or ignore the cache with no use cache. BigQuery's automatic caching is helpful, but sometimes you need more control. That is where materialized views come in. Materialized views let you pre-compute and store the results of complex or frequently used queries, making your data retrieval much faster and more efficient. Imagine you have a dataset called Video Game Example with a table named Scores. This table tracks players' names and their scores from classic arcade games. If you want to create a global leaderboard showing each player's highest score, you can write a select statement to group by player and find their top score. Embedding this query inside a Create Materialized View statement creates a view called Top Scores. This view stores the highest score for each player and updates automatically as new scores are added. Materialized views in BigQuery are always up to date. When the underlying scores table changes, the top scores view refreshes automatically. This means you can share real-time leaderboards or analytics without worrying about stale data. However, materialized views have some limitations. They do not support outer or self-joins, window functions, array subqueries, or non-deterministic functions. Still, they are a powerful tool for efficient, up-to-date data analysis in BigQuery. Lowering your BigQuery costs starts with understanding your pricing options. There are two main models, on-demand and capacity. Choosing the right one for your usage can make a big difference in your monthly bill. On-demand pricing is pay as you go. You are charged for the number of bytes processed by each query, and the first terabyte per month is free. Capacity pricing, on the other hand, is a fixed monthly fee based on reserved slots or virtual CPUs, letting you run unlimited queries within your slot limit. If you use BigQuery infrequently, on-demand is simple and cost-effective. Use the dry run feature to estimate costs before running queries, and set up maximum bytes build limit to avoid surprise charges. For heavy or predictable workloads, capacity pricing offers better control. Start with a small number of slots and scale up as needed. Consider multi-year commitments for discounts and schedule queries during off-peak hours to maximize idle slots. Regardless of your pricing model, regularly archive or delete unused data to reduce storage costs. Setting up data retention policies can automate this process, ensuring you only pay for what you truly need. Big data holds valuable insights, but making sense of it can be challenging. That is where data visualization comes in. Visualizations help us spot patterns, trends, and outliers that are hard to see in raw data, making decision-making easier. Looker Studio is Google's business intelligence platform designed for building and sharing dashboards and reports. It connects to hundreds of data sources, allowing you to present information in ways that are both informative and visually engaging. In this lesson, we focus on using BigQuery as a data source. There are two main versions, Looker Studio, which is free, and Looker Studio Pro, which requires a subscription. The Pro version offers enhanced enterprise features and technical support, but most users will find the free version more than sufficient for their needs. Looker Studio is a standalone product, separate from Google Cloud Platform. To access it, visit lookerstudio.google.com. You do not need a Google Cloud Platform account unless you want to use data stored in Google Cloud services like BigQuery. When you log in, you can create new reports or explore interactive tutorials. These tutorials showcase different charts and dashboards. You can use sample data or customize reports with your own data, making Looker Studio a flexible tool for visualizing information. If you have created a report in Looker Studio and want to share it, there are a few simple ways to do it. Let's walk through your options. First, you can export the underlying data from any chart. Hover over the chart, click the three-dot menu, and select Export. You can save the data as a CSV file, Microsoft Excel file, or Google Sheets. This exports only the data, not the visual chart. To share the full report, click the Share button. Enter email addresses or group aliases to invite viewers or editors. Assign the viewer role for view-only access or the editor role to let others make changes. Advanced options let you restrict editors from inviting others or prevent viewers from downloading or copying the report. You can also share via a link. Choose whether the link is public, unlisted, or limited to your organization. Public links are searchable on Google, while unlisted links are not. Organization-only links restrict access to coworkers. If someone shares a report with you, click the three-dot menu and select Make a Copy. You can use the same data source or switch to a new one. When you share a report in BigQuery, you are not just sharing the report itself. You're also sharing your connection to the underlying data source, which has important implications. Granting someone editor access means they can view all fields and records in the data source. Any queries they run will be charged to your Google Cloud Platform or GCP account. This makes sharing convenient, but it also means you could be responsible for unexpected costs. You can also share standalone data sources, making it easier to create multiple reports from the same dataset. However, sharing data sources requires caution to avoid exposing sensitive information. By default, reports use the creator's credentials. You can change this so the report uses the viewer's credentials instead. This way, viewers need their own access to the BigQuery dataset, and any charges will be billed to their GCP account, not yours. This helps protect your account from unwanted costs. Before sharing, always consider who should have access and how much access they need. Sharing can be risky if not managed carefully. Understand exactly what you are sharing and always prioritize data security. Thank you and see you in the next part. If you're not already subscribed, please subscribe to our YouTube channel. Check out our website for the latest real exam question and answers PDFs. Happy learning!